Okay, so imagine trying to have a conversation at a rock concert. It's almost impossible to hear anything over all that music. Well, scientists face a similar challenge when they're trying to measure super faint signals. It's like they get totally drowned out in a sea of interference. But you know what? They've got this clever tool. It's called a lock-in amplifier. And it helps them pluck those tiny signals right out of the noise. It's kind of like having a superpower, like being able to hear whispers even in the middle of a hurricane. We're going to deep dive today into an article by William L. Weaver. He published it back in January 2003 in Scientific Computing and Instrumentation, and it's packed with insights that are still super relevant even today.
Yeah, what's really cool is how Weaver starts with this simple concept, a visible absorption spectrometer, the kind you might have used back in high school chemistry.
Oh, yeah.
Huh.
I vaguely remember those. We used them to shine light through liquids, right? Like colored liquids.
Exactly. That's absorption spectroscopy in action. You shine a light through a sample, and some colors get absorbed, while others just pass right through. By analyzing which colors are absorbed and how much of each color, you can figure out what's in the sample.
So it's kind of like using light as a fingerprint to identify different substances.
Yeah, that's a great way to think about it. But here's the thing. Traditional absorption spectroscopy, it struggles when the signal you're looking for is really faint. It's like trying to see a single firefly. In a field full of fireworks, you just can't see the subtle light from the firefly because there's too much other light.
Okay, yeah, I see the problem. So where do lock-in amplifiers come in? Do they make the firefly brighter or something?
Not quite. Imagine if instead of the firefly's light being constant, it was flashing on and off at a specific rate. That's kind of what a lock-in amplifier does. It takes the signal you want and modulates it, basically turns it on and off at a specific frequency. We call that chopping.
Interesting. So instead of faint, continuous signal, it's more like a pulsing one. Why is that better?
Because now your signal has a unique fingerprint, that specific chopping frequency. And the lock-in amplifier is tuned to that exact frequency, so it becomes super sensitive to anything pulsing at that rate. But all the other noise and interference, that's not at that specific frequency. It gets ignored.
Oh, okay. I get it. It's like giving the firefly a special blinking pattern.
Yeah.
So you can easily spot it, even with all those fireworks going off.
Exactly. And you know what? This idea is super simple, but it's also incredibly effective. Lock-in amplifiers can detect signals that are millions of times weaker than the background noise.
Wow, that's amazing. So how did scientists even figure this out? Is this like a recent discovery?
Well, it might surprise you, but the basic principles behind lock-in amplification have actually been around for quite a while. Weaver's article from 2003 was kind of reflecting on the history of this tech. It's been used in research for decades.
So what's changed since then? Are lock-in amplifiers still relevant?
Oh, absolutely. In fact, they've become even more important. As scientists try to measure things more and more precisely, they need increasingly sensitive instruments.
So what's actually changed about the technology itself?
Well, one of the biggest advancements have been digital signal processing, or DSP. This lets us do much more sophisticated analysis of signals. And that's made lock-in amplifiers even more powerful and versatile.
Can you give us an example of a modern lock-in amplifier that uses this?
Sure. Weaver mentions the Stanford Research Systems model SR850 DSP LIA back in 2003. That was a cutting-edge instrument, and it's a great example of how powerful DSP can be. It can detect signals as small as 10 nanovolts.
Okay, hold on. How small is a nanovolt?
To give you an idea, that's like trying to detect the electrical signal from a single neuron firing in your brain. Or imagine trying to measure the faintest whisper from someone standing on the moon.
That's incredible. So this tech that started with shining light through colored liquids can now be used to, listen in on the activity of brain cells.
Exactly, and that's just scratching the surface. Lock-in amplifiers are used in all sorts of research, from studying the properties of materials at the atomic level to detecting incredibly faint signals from distant stars.
This is starting to sound like something straight out of a sci-fi movie.
It really is remarkable, and the most exciting part is we're only just beginning to tap into the potential of this technology as we continue to develop even more sophisticated signal processing and combine it with other cutting-edge advancements. Who knows what we'll be able to discover in the years to come. And here's where things get really exciting. Thinking about what future lock-in amplifiers might be capable of. What if? What if we could apply these principles, not just to physical signals, but to all the data we see every day?
Ooh, I like where you're going with this. You mean filtering out all the noise and misinformation online so we can get to the truth of things more easily?
Exactly. Imagine a world where we could use that same precision of lock-in amplification to go through like news articles and social media feeds, even scientific studies, anything. We could train algorithms to find and amplify the most reliable and relevant information and filter out all the noise and bias.
That would be revolutionary. It's like giving everyone their own personal BS detector.
It would definitely help us deal with all this information. It's so complex and overwhelming these days. And think about what it could do for scientific breakthroughs. We could analyze huge data sets from fields like genomics, climate science, astronomy, with incredible accuracy.
It's mind-boggling to imagine what we might discover. But let's come back to the present for a sec. You mentioned lock-in amplifiers are already used in a bunch of research areas. Can you give us some specific examples?
Absolutely. One area where they've been super important is in the development of MRI. You know those scans that let doctors see inside the body without surgery? Well, MRI relies on detecting these super faint signals from the body's tissues. And without lock-in amplifiers, those signals would be completely lost in the noise.
So lock-in amplifiers helped unlock the secrets of the human body. That's amazing.
It really is. And it doesn't start there. Lock-in amplifiers are also essential in materials science. They help researchers study the properties of materials at the atomic level, revealing how they react to things like light, heat, and stress. This knowledge is then used to design new materials with specific properties like stronger, lighter, more conductive, you name it.
So from medical imaging to material science, these little devices are having a big impact. What other fields have been touched by this technology?
Oh, the list goes on and on. They're used in environmental monitoring to find tiny amounts of pollutants in the air and water. They're used in astronomy to study the faint light from distant galaxies. They're even being used to develop super-sensitive detectors for gravitational waves, those ripples in space-time that Einstein predicted.
Wow. It's like lock-in amplifiers are the unsung heroes of scientific discovery.
They definitely deserve more recognition. But let's not forget the human element behind all of this. As impressive as lock-in amplifiers are, they're just tools. It's the scientists and engineers, the curious minds asking the questions and designing the experiments, who are driving these incredible discoveries.
That's a good point. It's the combination of human ingenuity and technological innovation that really pushes the boundaries of what's possible.
Exactly. And as we keep developing more powerful tools and asking bolder questions, I have no doubt the future of scientific discovery will be even more amazing than we can imagine.
It's funny, as we've been talking about all these uses of lock-in amplifiers, it's really hit me how this simple idea of filtering out noise has led to these huge advancements in so many fields.
Yeah, it really makes you think about what other signals we might be missing in our own lives, just because we're overwhelmed by noise.
That's a really good point. I mean, think about all the information we deal with every day. The news, social media, all those notifications and distractions. It's like we're all living in that rock concert you mentioned, struggling to hear anything.
Exactly. And just like those scientists, we need to figure out our own ways of filtering out the noise and focusing on what really matters. What are our goals? What values are important to us? What information will actually help us grow?
It's almost like we need our own personal lock-in amplifiers for our lives.
Yeah.
But how do we even do that? It seems like the noise is just getting louder.
Well, I think it starts with being aware of where the noise is coming from, Are there certain social media accounts that always leave you feeling drained? Or news outlets that just focus on sensationalism? Once you know where the noise is, you can start tuning it out.
Right. And then we can be more intentional about where we focus our attention. Maybe spend less time on social media and more time reading or having real conversations or just enjoying some quiet.
That's it. It's about choosing what you focus on. And those positive things can have a huge impact on your creativity, your well-being.
It's a good reminder that we have more control than we think. We don't have to just be bombarded by all this noise. We can choose what we pay attention to.
Absolutely. And just like those scientists, we can use these same principles to unlock our own potential.
This has been a really interesting deep dive. It's amazing how this one scientific instrument can teach us so much about how we live our lives.
I agree. It shows us that even complex science can have really practical lessons.
Well, a huge thank you to you for sharing your insights with us.
It was my pleasure.
And to our listeners. We hope this deep dive got you thinking about how to be more mindful of the signals you choose to amplify. Until next time, keep exploring and keep seeking out what matters most.